Module 3, Lecture B, Numerical Methods. By the end of this lecture, you will be able to implement simple iterative methods for solving engineering equations, evaluate convergence behavior using tolerances and iteration limits, and package numerical procedures into reusable Python functions. Bisection root finding. Bracket the root. Bisection root finding begins by choosing a lower and upper value that bracket the root. The function must have opposite signs at these two values, which suggests a crossing between them if the function is continuous. This interval does not give the exact solution, but it reliably narrows where the root must be, which is useful in engineering balance problems such as heat flow or pump pressure. Choosing a good bracket requires both math insight and practical judgment. Test the function at reasonable values and look for a sign change, which shows a root lies between them. The bracket should be large enough to contain the root, but not so large that the method wastes time narrowing the interval. In the bisection method, bracketing is essential because it keeps the search within an interval known to contain a root, making the method reliable. This guarantee depends on the function being continuous, since a sign change only proves a crossing when there are no breaks or jumps. Engineers should also use physical reasoning and estimates, because multiple roots or roots without a sign change can make the interval misleading. Python code. Bracket the root. This example identifies an interval that contains an engineering root. Opposite signs at the interval ends show that the function crosses 0, so bisection can be applied. The net flow error function compares the actual flow rate with the target flow rate. It subtracts the target from the actual value to show how far the system is from the desired flow, which helps guide flow balancing. Two trial flow rates are chosen to define the search interval: 35 liters per minute as the lower bound and 80 liters per minute as the upper bound. This interval is then used to check whether the function's root is bracketed, which is required for the bracketing method. Set the target flow rate to 52 liters per minute. Then compare the lower and upper trial flow rates against this target using the net flow error function. The resulting errors show how far each trial is from the desired flow. If the two errors have opposite signs, the target crossing is bracketed between the trial flows. To check whether a root is bracketed, compare the signs of the function values at the lower and upper flow rates. If their product is negative, the signs are opposite and the interval contains a bracketed root. The result is marked as a valid bracket or not bracketed, indicating whether the interval is suitable for a method like bisection. The output reports whether a flow balance interval is properly bracketed for the bisection method. It shows the lower and upper flow rates with their function values, then states whether the endpoint signs make the interval valid for bisection. The code first checks whether a valid bracket has been found, meaning the root is between the lower and upper flow rates. If so, it reports that interval, confirming that the bisection method can be used to locate the root. This example shows a failed bracketing case by choosing a lower flow rate of 10 and an upper flow rate of 30. The root is not properly bracketed because the function values at these 2 points do not have opposite signs. Without that sign change, methods like bisection cannot use the interval as a valid bracket. To test the second trial interval, we compare the flow rates at its lower and upper boundaries with the target flow. The net flow error function gives the difference for each boundary. If these two differences have opposite signs, the interval brackets a root. To check whether an interval contains a root, multiply the function values at its lower and upper ends. If the product is less than 0, the signs are opposite, so the interval is a valid bracket. Otherwise, the root is not bracketed, and the interval is not suitable for methods such as bisection. The code prints a short summary of a second trial interval, showing its lower and upper bounds as whole numbers, and reporting whether it forms a valid bracket. That status is based on whether the function values at the two bounds have opposite signs, which indicates that a root lies between them. This script tests whether two trial flow rates bracket a root for a tank balance calculation by comparing each rate with a target flow rate. A valid bracket occurs when the two results have opposite signs, meaning the root lies between them. The example shows that 35 and 80 liters per minute successfully bracket the target of 52, while 10 and 30 do not. This feedback helps decide whether an interval is suitable for methods such as bisection. Root interval. In bisection root finding, you begin with an interval where the function changes sign, which indicates that a root lies between the endpoints. The method repeatedly halves this interval to reduce uncertainty and improve the estimate. For engineering problems, this turns a broad possible range, such as a critical temperature, into a more precise solution. To update a root interval, test the function at the midpoint and compare its sign with the signs at the endpoints. Keep the half where the sign changes, moving the opposite endpoint to the midpoint. This preserves an interval that contains the root while cutting the search range in half, as in engineering problems where midpoint tests help narrow possible solutions. The bisection method works by cutting the root interval in half at each step, making its progress easy to track and reliable. The interval's width shows the remaining uncertainty. A wide interval means the root is only roughly located, while a narrow one gives greater precision. Although it is not the fastest method, bisection is useful because it turns equation solving into a steady process of narrowing the search area and measuring confidence in the result. Python code, root interval. The bisection method finds roots by keeping a reliable interval that contains the solution. Each midpoint test cuts the remaining uncertainty in half, making it useful for engineering equations that need dependable brackets. The residual function represents a simple engineering balance using the flow rate in gallons per minute. It squares the flow rate and subtracts 100, and the goal is to find the flow rate that makes the result equal to 0. This is a typical way to solve for a value that satisfies a balance condition. We begin the bisection method by choosing an initial interval from 5 to 15. These endpoints define the range where we will search for a root. This interval should contain a sign change in the function, which suggests that a root lies between the two values. Evaluate the residual function at both the left and right endpoints to find the sign of the function at each end. If the signs differ, the function changes sign across the interval, which indicates that a root is bracketed between the endpoints. The code first checks whether the function values at the two endpoints have opposite signs. If they do not, it raises an error because the interval may not contain a root. This check is essential for the bisection method, which depends on a sign change to guarantee a root lies between the endpoints. The code prints a heading for the bisection method output, labeling each iteration with its left endpoint, right endpoint, and interval width. This makes it easy to follow how the interval containing the root becomes smaller over time. The loop runs 6 times to improve the root estimate. Each time, it takes the average of the interval endpoints as the midpoint, evaluates the residual there, and uses that result to choose which half of the interval still contains the root. This code keeps the half of the interval that still brackets the root. It checks whether the function changes sign between the left endpoint and the midpoint. If it does, the right endpoint becomes the midpoint. Otherwise, the left endpoint becomes the midpoint. This preserves an interval where the root must lie. To track progress in the bisection method, we measure the interval width by subtracting the left endpoint from the right endpoint. Printing each iteration's number, endpoints, and width shows how the interval shrinks over time. This makes the increasing precision of the root estimate easier to see. To finish the bisection method, we average the current left and right endpoints to estimate the root. This midpoint is the best approximation within the interval, and the resulting flow rate is reported to 3 decimal places. This script uses the bisection method to estimate the root of a quadratic engineering balance function. It begins with an interval from 5 to 15, where the endpoint values have opposite signs, so a root must lie inside. Each iteration tests the midpoint and keeps the half of the interval that still contains the root, reducing the uncertainty over 6 iterations. The final estimate is the midpoint of the last interval, giving an approximate flow rate in gallons per minute. Tolerance criteria. In bisection root finding, tolerance sets the stopping point for when an estimate is accurate enough. The method repeatedly halves an interval that contains the root, so the error decreases in a predictable way. Because different problems need different levels of accuracy, the tolerance should match the practical requirement, such as a looser setting for a phase change estimate and a tighter one for a structural calculation. In the bisection method, tolerance is often based on the size of the interval containing the root, since a smaller interval gives a clearer bound on uncertainty. Another option is to check whether the function value at the midpoint is close to 0. These criteria can lead to different results because flat or steep functions affect how function values relate to input accuracy. In practice, engineers choose tolerances that fit the behavior of the specific system. In the bisection method, tolerance should balance accuracy, effort, and reliability. If it is too loose, the method may stop too early and give unreliable results. If it is too tight, it may waste computation beyond the quality of the data. A practical tolerance should match the scale and uncertainty of the problem, and it should be used with a maximum iteration limit to prevent unexpected issues. Python code. Tolerance criteria. Bisection tolerance sets the accuracy needed for an engineering calculation, such as solving a simple pressure equation. Iteration limits help keep the numerical process controlled and prevent excessive computation. The pressure residual function measures how far a volume's cubed value is from a target of 10. It returns the difference between the cube of the volume in liters and 10, representing the remaining error in an engineering calculation. This kind of residual is commonly used in numerical methods to guide an iterative solution towards 0. The bisection solver finds a root of a function within a chosen interval, using a specified accuracy tolerance and maximum number of iterations. It first evaluates the function at both interval endpoints to check whether the signs differ. If the values have the same sign, the root is not properly bracketed, so the solver raises an error instead of continuing. The code first checks whether the starting interval actually brackets a root. It evaluates the function at both endpoints, and if the results have the same sign, the function may not cross 0 within that interval. In that case, it raises an error and requires the interval to be adjusted so one endpoint is positive and the other is negative. The algorithm repeats up to the allowed number of iterations. Each time, it finds the midpoint of the current interval as the latest estimate of the root, then evaluates the function there. That value guides how the interval will be adjusted next. The code measures the current uncertainty by taking half the width of the interval. If this uncertainty is within the chosen tolerance, it stops and returns the midpoint as the estimated root, along with the iteration count, the uncertainty value, and the function value at that midpoint. This step chooses which half of the interval to keep in the next iteration. If the function values at the lower bound and midpoint indicate a root between them, the upper bound is moved to the midpoint. The function value at the upper bound is updated as well, keeping the narrowed interval accurate for the next check. If the midpoint does not show a root in the lower half, move the lower bound up to the midpoint. The root is then assumed to lie in the upper half, and the stored function value at the lower bound is updated for the next iteration. When the iteration limit is reached, the bisection method uses the midpoint of the final interval as the best estimate of the root. It also reports the interval's half-width as the remaining uncertainty, along with the number of iterations used and the function value at that midpoint. Together, these values summarize the final result of the process. We compare tolerance levels for solving the pressure equation with the bisection method. The solver uses the pressure residual as its target, starts with bounds of 1 and 3, and allows up to 50 iterations. With a loose tolerance of 0.05, the solution may be less precise, but should require fewer iterations, showing the trade-off between accuracy and computation. We use the bisection solver to find the root of the pressure residual function, starting with a bracket from 1 to 3 liters. A very small tolerance is set to make the result highly accurate, with a limit of 50 iterations to stop the search if it does not converge. This setup favors precision, but it may take more iterations than a looser tolerance. The output compares bisection results for solving volume cubed minus 10 equals 0 using loose and tight tolerances. For each tolerance, it reports the estimated root, the number of iterations, and the uncertainty, formatted consistently. The main point is that tighter tolerance gives a more accurate root estimate, but it also takes more iterations. This script uses the bisection method to find the root of a cubic pressure volume equation. It compares a loose tolerance with a tight tolerance, showing that a looser setting reaches an answer in fewer iterations but with less precision. A tighter tolerance takes more iterations but produces a more accurate result, demonstrating the trade-off between speed and accuracy. Iteration control. Tolerance criteria. Tolerance criteria tell an iterative numerical method when to stop by defining how accurate the result needs to be. Since engineering problems often do not require exact answers, a method can stop once changes in the solution or estimated error are small enough for the task. This balances accuracy with computational effort and avoids unnecessary or endless calculation. Tolerance should be chosen to fit the scale, risk, and accuracy needs of the engineering problem. A loose tolerance can make results unreliable, while an overly strict one can waste time and expose computational limits. Good tolerance choices depend on the physical context, the quality of the data, and how precise the final decision needs to be. Tolerance criteria are used to judge whether an iterative method is settling toward a stable result. Meeting a tolerance can suggest convergence, but it does not guarantee the solution is correct, especially if the method, starting point, or problem has issues. Engineers, therefore, check for consistent signs, such as small changes between iterations and agreement with the original problem. Good tolerance choices balance confidence, practicality, and the needs of the engineering context. Python code. Tolerance criteria. Tolerances define when an iterative process is accurate enough to stop, while residuals show how much mismatch remains in the engineering equations. Iteration limits add a safety stop to prevent numerical work from continuing endlessly. The script imports the math library so it can use built-in mathematical functions and constants. This supports calculations such as logarithms and square roots, which are needed for accurate engineering equations and physical modeling. The function defines a bisection solver for finding a root within a given interval. It uses the target function, the interval bounds, a stopping tolerance, and a maximum iteration limit. It first evaluates the function at the lower bound to get a residual, which helps guide the search and check whether the root is likely within the interval. The code evaluates the function at the interval's upper bound and compares its sign with the lower bound result. If both residuals have the same sign, the interval does not bracket a root, so the bisection method cannot proceed. In that case, the code raises an error to require an interval that contains one root. The process begins by creating an empty record to track each bisection step, including the iteration count, midpoint, residual, and interval width. The algorithm then repeats up to the allowed number of iterations, each time finding the midpoint between the current lower and upper bounds. This midpoint serves as the current estimate of the root. In each bisection iteration, the code evaluates the function at the midpoint to measure the residual and see how close the guess is to a root. It also computes half the distance between the current bounds to track how narrow the interval has become. These values, along with the iteration number and midpoint, are stored as a record for later review or debugging. The code stops when the residual at the midpoint is within the chosen tolerance, meaning the current estimate is accurate enough. It then returns the midpoint as the estimated root, the iteration count, the reason for stopping, and the saved iteration history for review. The code stops when the current interval is within the chosen tolerance, meaning the root estimate is precise enough based on interval size. It then returns the midpoint as the estimated root, along with the iteration count, a note about the stopping reason, and the iteration history. This avoids extra calculations once the interval is sufficiently small. The code checks whether the residual changes sign between the lower bound and the midpoint, which indicates the root is in that part of the interval. If so, it moves the upper bound to the midpoint, narrowing the search range. It also updates the upper bound residual to match the midpoint residual for the next iteration. If the residuals at the lower bound and midpoint do not indicate a sign change, the root is not in that lower half of the interval. The method then moves the lower bound up to the midpoint and updates its residual value. This narrows the search to the correct half, helping the algorithm move closer to the root. If the tolerance is not met before the iteration limit, the function stops and returns the interval midpoint as its best estimate. It also reports the number of iterations, marks the reason as an iteration limit, and includes records of the midpoint, residual, and interval width from each step to help review convergence. The Colebrook residual function models the pipe friction factor using the Colebrook equation. It sets the pipe surface roughness to a small value, 0.00015, which is an important input for friction factor calculations in fluid dynamics. The pipe diameter is set to 0.25 meters, and the Reynolds number is set to 100,000 to represent the flow condition. The calculation then evaluates 1 divided by the square root of the friction factor, which is the left side of the Colebrook equation for turbulent pipe flow. The function evaluates the residual of the Colebrook equation to help find the friction factor. It builds the right-hand side from a roughness to diameter term and a Reynolds number term involving the square root of the friction factor. Then returns the left term plus twice the base 10 logarithm of that combined value. We test the bisection solver for the Colebrook equation under 3 settings to compare accuracy and limits. A loose tolerance gives a faster, moderately accurate result, while a much stricter tolerance aims for higher precision with the same iteration limit. A final run uses an extremely strict tolerance, but only 5 iterations, showing how a low iteration cap can prevent the solver from reaching the desired precision. The output summarizes Colebrook friction factor calculations using the bisection method under different stopping settings. It reports the friction factor, iteration count, and stopping reason for loose tolerance, strict tolerance, and a case where the iteration limit is reached. This comparison shows how tolerance choices affect both the result and the efficiency of the method. To judge the engineering significance of the results, we compare the final Colebrook residuals for each tolerance setting. We take the absolute residual for the loose tolerance, the strict tolerance, and the limited iteration case. These values show how closely each computed friction factor satisfies the governing equation. The code reports residual magnitudes for loose, strict, and iteration-limited tolerance settings. These values, shown in scientific notation, indicate how close each solution comes to satisfying the Colebrook equation. Comparing them shows how tolerance choice and iteration limits affect solution accuracy. This script solves the Colebrook equation for fluid friction factors using the bisection method. It tests loose and strict tolerances, as well as a case with too few allowed iterations, to show how the stopping rule affects the result. The tolerance-based cases stop when the residual is small enough, with the stricter setting taking more iterations, while the limited case stops because it reaches the iteration cap. The reported residuals show how closely each computed friction factor satisfies the equation. Tolerance criteria. Tolerance criteria tell an iterative numerical method when to stop. They define an acceptable level of error, so the process ends once estimates change very little or satisfy the governing equations closely enough. This gives engineering calculations results that are accurate for practical use without wasting time on unnecessary precision. Choosing a tolerance depends on the scale of the problem, the sensitivity of the application, and the cost of error. Absolute tolerance uses a fixed cutoff and works best when values share a consistent scale, while relative tolerance judges the change compared with the value itself, which is better for very large or very small numbers. A good tolerance balances accuracy with practical computing effort, so results are reliable without unnecessary cost. Tolerance criteria help judge whether an iterative method has converged reliably, especially when there is also a limit on the number of iterations. If the tolerance is met quickly, the method is likely working efficiently for that problem and starting point. If it is not met before the iteration limit, the result should be treated cautiously because the tolerance may be too strict or the initial guess may be poor. Reporting whether convergence occurred is therefore both a stopping rule and a quality check for tools such as pipe diameter design calculations. Python code, tolerance criteria. Iteration control requires clear stopping rules. Tolerances decide when numerical estimates are close enough, while limits keep engineering calculations from running endlessly. A fixed point solver finds a value that stays the same when a function is applied to it. It starts with an initial estimate, converted to a floating point number for accurate calculation, then repeatedly refines that estimate. At each step, it checks whether the change is smaller than the chosen tolerance, stopping when the process has converged or when the maximum number of steps is reached. The solver begins by creating a record of iteration progress, including each step's estimate and value changes. It also sets a convergence flag to false, showing that the required tolerance has not yet been met because the iteration process has not started. The loop repeatedly updates an estimate to find the square root of 25 using fixed-point iteration. Each step averages the current estimate with 25 divided by that estimate, then uses the result to check whether the process is converging. To track convergence, first measure the absolute change as the difference between the new estimate and the current estimate, ignoring sign. Then find the relative change by comparing that amount to the size of the new estimate. A very small lower limit is used in the denominator to prevent division by zero. The code records each iteration by saving the step number, updated estimate, absolute change, and relative change for later analysis. It then replaces the current estimate with the new one, allowing the iterative process to keep refining the solution. The code checks whether the change between the new estimate and the current estimate is smaller than the chosen tolerance. If so, the solution is considered precise enough, and the solver marks that it has converged. It then exits the loop to avoid any unnecessary further calculations. The function returns the final estimate from the fixed-point iteration, along with a convergence flag showing whether the tolerance was met. It also returns the iteration history, which records each step's estimate and its absolute and relative changes. This makes it possible to review both the result and how the sequence behaved as it approached convergence. We run the fixed-point solver with a relaxed tolerance, starting from 2.0 and allowing up to 20 steps. The solver returns the final estimate, whether it converged, and the iteration history, which are stored for later use. The fixed-point solver is tested with a starting value of 2, a very strict tolerance, and only 4 allowed steps. Its output gives the final estimate, whether it converged within the tolerance, and a history of the iterations. This history shows how the estimate changed at each step, helping evaluate the solver's behavior under demanding precision settings. The output reports the result of using fixed-point iteration to solve x squared equals 25. It states whether the relaxed tolerance case converged, shows the final estimate to 6 decimal places, and gives the number of iterations based on the recorded history. For the strict tolerance case, we check whether the method converged, then report the final solution estimate to 6 decimal places. We also show how many iterations were needed, giving a concise view of both the result and how efficiently it was reached. We inspect the final entry in the strict tolerance history to see the last iteration's result. The absolute change from that step is displayed in scientific notation, making it easy to judge how little the estimate changed and how much precision the strict tolerance achieved. This script uses fixed-point iteration to approximate the solution to x squared equals 25, starting from an initial guess of 2. Pause. With a relaxed tolerance and enough allowed iterations, the method converges to a value close to 5. With a much stricter tolerance but only 4 iterations, it stops before converging, showing how higher precision can require more computation. The output reports convergence status, the final estimate, iteration count, and the last change in the strict case. Convergence criteria. Convergence criteria tell us when an iterative numerical method is close enough to a reliable solution to stop. Instead of requiring an exact answer, they check whether changes in the approximation, remaining error, or function behavior are small enough for the engineering task. The main goal is numerical stability and a solution that is sufficiently accurate for practical use. A convergence criterion should match both the numerical method and the physical purpose of the problem. If it is too loose, the calculation may stop before the results are dependable. If it is too strict, it can waste computation or run into precision limits. The right tolerance depends on how the results will be used, such as whether they support early exploration or final safety decisions. So it should be chosen deliberately rather than left to defaults. Iteration limits help prevent numerical methods from running forever when they fail to converge. If the limit is reached, the result should be treated with caution because the initial guess, scaling, tolerance, or method may need adjustment. Good convergence control makes numerical results more reliable and helps engineers see when a method needs to be changed. Python code convergence criteria. Iteration control keeps numerical calculations from running endlessly. Convergence tolerances set the level of accuracy considered acceptable in engineering work, while iteration limits help identify searches that have failed to converge. The bisection solve function finds a root of a given function using the bisection method. It takes the function, lower and upper interval bounds, a convergence tolerance, and a maximum iteration limit. It first evaluates the function at both bounds to check whether the interval brackets a root, which is required for the method to work. The code verifies that the chosen interval is valid for the bisection method. If the function values at the two bounds have the same sign, the interval does not bracket a root, so the code raises a value error. This prevents the method from starting unless a root is guaranteed to lie within the interval. The process begins by creating an empty history list to record key details from each iteration, including the midpoint, interval width, and function value. Then, the initial midpoint is found by averaging the lower and upper bounds, giving the bisection method its starting point for narrowing the interval that contains the root. The process repeats up to the chosen maximum number of iterations. In each pass, it finds the midpoint between the current lower and upper bounds and treats that point as the current root estimate. The function is then evaluated at this midpoint, and the result guides how the interval should be narrowed for the next iteration. The code measures the current interval width using the distance between its high and low bounds, which shows how close the search is to the root. It then records the iteration number, midpoint, interval width, and function value at the midpoint in a history list. The code stops when the interval is narrow enough or the function value at the midpoint is close enough to 0. This means the root estimate has reached the required accuracy. It then returns the midpoint, the iteration count, a success indicator, and the iteration history for review. This part of the bisection method checks whether the root is between the current lower bound and the midpoint. If so, the upper bound is moved to the midpoint, narrowing the search to the lower half of the interval. The midpoint's value is also stored as the new upper value for the next iteration. If the lower value and midpoint value do not have opposite signs, the root is not in the lower half of the interval. So, the lower bound is moved to the midpoint, narrowing the search to the upper half and setting up the next iteration. If the method reaches the maximum number of iterations without converging, it returns the current midpoint as the best root estimate. It also reports that the iteration limit was reached, marks convergence as false, and includes the iteration history with the midpoint estimates and interval widths. This function estimates a pipe diameter condition using the diameter in meters. It calculates a flow-related term by dividing 0.04 by the diameter raised to the fourth power. So smaller diameters greatly increase resistance. the function returns this term minus 2500, which can be used to find the diameter where the flow term balances the constant. The bisection solver is used to find the root of the pressure balance equation within the interval from 0.05 to 0.20. It uses a tolerance of 1 times 10 to the negative 5 and allows up to 40 iterations to control accuracy and prevent an endless search. The solver returns the estimated root, the number of steps taken, whether it converged, and the iteration history. Here, the pressure balance equation is solved with the bisection method using a narrow interval from 0.05 to 0.20, a very small tolerance, and only 5 allowed iterations. This restrictive setup shows what happens when the iteration limit is too low for the method to converge. The results compare 2 runs of the bisection solver. First, the output reports whether the initial run converged, how many iterations it needed, and the estimated diameter to 5 decimal places. It then reports the same information for a second run with stricter tolerance but fewer allowed iterations. Finally, it shows the last few interval widths from the successful run to illustrate how the solution narrowed near the end. The code summarizes convergence by showing the final few iteration records. For the last 3 entries, it reports the iteration number, the current root estimate, the interval width, and the residual. The interval width and residual are printed in scientific notation, giving a compact view of how the solution behaved near the end. This script uses the bisection method to estimate the pipe diameter that makes a flow equation equals 0. With a practical tolerance and enough iterations, the method converges and reports the estimated diameter and iteration count. A second run uses an overly strict tolerance with too few iterations, so it fails to converge, showing why solver settings must be realistic. The output also summarizes recent successful iterations by showing how the interval narrows and the residual decreases. Reusable solver functions. Solver structure. A reusable solver should have a clear, predictable structure because numerical methods repeat the same basic pattern. It takes the information that defines a problem, runs an iterative process, and returns results other parts of a program can use. For example, a pipe network solver might need a relationship function, an initial guess, a tolerance, and an iteration limit. The goal is for users to apply the solver confidently without needing to understand its internal details. A solver usually follows a simple iterative structure. Set an initial guess, repeat updates, check whether the result is close enough to the target, and then return the final answer. This same pattern applies across tasks like nonlinear equation solving or force balancing. Because the framework is consistent, solvers are easier to understand, adapt, and maintain. A good numerical solver should report not only the final answer, but also whether it converged, how many iterations it used, and how close it came to the desired tolerance. This information helps engineers judge whether a result is reliable for design decisions. If the solver stops because it reaches an iteration limit, it should make that clear so the user can adjust the starting guess or method. Python code solver structure. Reusable solvers simplify repeated numerical work by wrapping common steps into a reusable structure. In this example, a solver handles a pressure equation and returns both the computed value and its status. The fixed point solver function finds a stable solution by repeatedly improving an initial guess. It takes an update rule, a starting value, a tolerance, and a maximum number of iterations. The starting value is converted to a floating point number for precision, and the change between guesses is tracked so the loop can stop when the solution is accurate enough or the iteration limit is reached. The loop runs up to the maximum number of iterations. Each time, it uses the update function to produce the next guess, then measures how much that guess changed by taking the absolute difference from the current one. This code checks whether the solution has converged by comparing the current guess with the previous one. If the change is within the allowed tolerance, the solution is considered stable. The function then returns the current guess, the number of iterations used, a convergence indicator, and the size of the final change. This step replaces the current estimate with the next one, so the iterative method can keep improving the solution. Each pass then uses the most recent estimate, helping the process move closer to convergence. If the solver reaches the iteration limit without converging, it returns the current guess as the best available estimate. It also reports that the maximum iterations were used, marks convergence as unsuccessful, and includes the final change to show how close the last update came to the tolerance. The pressure update function estimates the next pressure drop in a pipe from the previous one. It combines a constant base drop of 12 with 1/4 of the previous pressure drop. This represents both a fixed pressure effect and a smaller effect carried over from the past state. The solver begins with an initial pressure drop of 0. It uses a tolerance of 0.001 to decide when the solution has converged, stopping once changes are smaller than that threshold. A maximum of 25 iterations is also set to prevent the solver from running indefinitely. The fixed point solver is started with the pressure update function, an initial pressure drop of 0, a convergence tolerance, and a maximum iteration limit. Using these settings, it repeatedly updates the pressure drop until it reaches a stable estimate or the iteration limit is reached. The solver's output is separated into key results, including the pressure drop, iteration count, convergence flag, and final change. The program then reports whether the run converged or stopped early, making the solver's outcome easy to interpret. The output gives a compact report on the reusable fixed-point solver. It states whether the solver converged, shows the estimated pressure drop, reports how many iterations were needed, and gives the final change in pressure drop. Together, these values help judge the accuracy and computational effort of the solution. This script shows a reusable fixed-point solver for estimating pressure drop in a pipe. Starting from 0, it repeatedly updates the estimate until the change is small enough or the iteration limit is reached. The pressure drop model adds a base value to a fraction of the previous estimate. When run, the solver reports successful convergence, the estimated pressure drop, the iterations used, and the final change. Reusable solver design. Reusable solver design means building a numerical method that works across many engineering problems with only minor changes. A good solver accepts the needed data, carries out the calculations internally, and returns results in a consistent way. Because different problems often share the same computational patterns, this lets engineers separate the mathematical model, the numerical method, and the interpretation of results. A reusable solver should have a clear interface that states its required inputs and expected outputs. Important settings such as initial estimates, convergence tolerance, and iteration limits should be explicit rather than hidden or hard-coded. This makes the solver adaptable, so different engineering problems can be handled by changing inputs instead of rewriting the core procedure. A reusable solver should report more than the final answer. It should also show whether it converged, how many iterations it used, and how closely it met the tolerance, so users can judge the result's reliability. This transparency matters in professional applications where an answer may affect safety or cost, and it helps make the solver easier to validate maintain, and integrate into larger systems. Python code, reusable solver design. Reusable solvers keep numerical methods separate from specific models, making engineering calculations easier to adapt. Clear inputs support flexible use, while returned diagnostics help assess how well the solver converged. This means the code does not need any extra packages to run. It relies only on Python's built-in features, so it is self-contained and easy to execute in a standard Python environment. We define a reusable fixed-point solver that finds a solution by repeatedly improving an estimate. It uses an update rule, a starting guess, a tolerance for when the estimate is accurate enough, and a maximum number of attempts. By changing these inputs, the same solver can be adapted to many engineering calculations. The process begins by using the initial guess as the starting estimate and converting it to a floating point value for accurate calculations. The error is then set to infinity, so the iterative loop runs at least once and can begin improving the estimate. The loop runs from the first iteration up to the allowed maximum, controlling how many times the solver refines its estimate. It stops early if the solution reaches the required tolerance, or ends when the iteration limit is reached. Each pass uses the update function to try to improve the estimate. The code uses the update function to produce a new estimate from the current one, then converts it to a floating point value for precise calculation. It measures the error as the absolute change between the two estimates, which shows how much the estimate has shifted and helps judge whether the iteration is converging. This code checks whether the change between the new estimate and the current estimate is within the allowed tolerance. If the change is small enough, the solution is considered converged. The solver then returns the new estimate, a success indicator, the iteration count, and the final error, allowing it to stop early once the result is accurate enough. The current estimate is replaced with the new estimate, so the iteration can continue using the latest result. This lets the solver keep refining its answer and move closer to convergence. If the function does not converge, it returns the last estimate, a false convergence flag, the maximum number of iterations reached, and the final error. Together, these values show that the method stopped without meeting the desired tolerance and indicate how close the last estimate was. This function estimates pipe flow from a pressure drop model. It uses a target pressure drop of 8 psi and a constant coefficient of 0.015. Then returns the flow estimate found by taking the square root of the pressure drop divided by that coefficient. The calculation uses a target pressure drop of 8 psi and a coefficient of 0.015. Together, these values model how pipe flow relates to pressure drop and are used to update the flow estimate. The code updates the flow estimate by using the target pressure drop and a coefficient. It divides the pressure drop by the coefficient, takes the square root of that value, and returns the result as the new flow estimate. The tank depth update function estimates tank depth from a simple volume relation. It uses a fixed tank volume of 12 cubic meters and a base area of 3 square meters, then finds the depth by dividing volume by area. The input depth value is accepted, but not used, and the function returns an updated depth of 4 meters. The code defines a tank volume of 12 cubic meters and a base area of 3 square meters. It then finds the liquid depth by dividing the volume by the base area, giving the height of the liquid column in meters. The function updates the tank's depth by dividing its volume, 12 cubic meters, by its base area, 3 square meters. The fixed point solver is used for two engineering calculations. First, it finds the pipe flow rate needed to reach a target pressure drop, starting from an initial guess of 10. Then it estimates tank depth from volume and area, starting from an initial guess of 1. In both cases, the solver reports the final estimate, whether it converged, how many iterations it used, and the final error. The solver results are unpacked for both the pipe flow and tank depth problems. For each case, the code extracts the final value, whether the method converged, how many iterations it used, and the final error. This makes the outputs easier to read and use later in the program. The output summarizes a reusable fixed-point solver applied to two engineering problems, pipe flow and tank depth. For each case, it reports the computed result, whether the solver converged, the number of iterations, and the final change in the estimate. This gives a concise view of both the solution values and the solver's performance. This script shows a reusable fixed-point iteration solver for two engineering models. It updates an estimate until the change is small enough or the iteration limit is reached. In a pipe flow example, it converges from 10 to about 23 gallons per minute, and in a tank depth example, it converges from 1 meter to 4 meters. The printed results report the final value, convergence status, iteration count, and final error, demonstrating that the same solver can handle different models and provide useful diagnostics. Error handling. Reliable numerical solvers need clear error handling, not just smooth execution. They should detect problems such as invalid inputs or failure to converge, then report them clearly. For example, a heat exchanger calculation should reject negative heat capacity because it makes the result meaningless. These checks help engineers build safer and more reusable tools. A reliable solver should clearly separate input errors from iteration warnings. Invalid inputs should stop the calculation and explain the problem, while issues like slow convergence or reaching the iteration limit should be reported even if an estimate is produced. This clarity helps engineers judge results, adjust settings, or reconsider whether the model is appropriate. Clear error handling makes solver functions more reliable and easier to use in larger automated workflows. When a solver detects impossible or unstable inputs, it can report the problem, record the failure, and prevent invalid results from being treated as valid solutions. This supports responsible numerical computing by keeping diagnostic information tied to the final interpretation of results. Python code, error handling. Build reusable solvers that validate engineering inputs before starting iteration, fail clearly when something is wrong, and return useful status information along with estimates. The heat balance residual function checks an energy balance for a fluid. It uses temperature, mass flow rate, specific heat capacity, and heat transfer to estimate the energy carried by the fluid, then subtracts the expected heat transfer. The remaining residual shows how far the calculated energy is from the heat transfer value, helping identify imbalance in a thermal system. The bisection solver function finds a root of a given function using the bisection method. It receives the function, lower and upper search bounds, a tolerance for accuracy, a maximum iteration limit, and any extra function inputs. Before running, it checks that the tolerance is positive and that at least one iteration is allowed. If not, it raises an error to prevent the solver from using invalid settings. The code verifies that the maximum iteration setting is an integer because the solver needs a whole number to control its loop. If the input is not an integer, it raises a type error so the user can correct it. This helps prevent unexpected behavior during execution. The function is evaluated at both the lower and upper bounds, using any needed extra arguments. These two values are then used to check whether the function changes sign across the interval, which is required for the bisection method to work correctly. This code checks whether the function values at the two bounds have the same sign. If they do, there is no sign change, so the bisection method cannot guarantee a root between the bounds. In that case, it raises an error to indicate that the chosen bounds are invalid. The loop repeats up to the allowed number of iterations, each time using the average of the lower and upper bounds as the current root estimate. The function is evaluated at this midpoint to check how close it is to a root. The error estimate is then found as half the width of the current interval, which indicates whether the approximation is within the required tolerance. The code checks whether the midpoint is accurate enough to stop the iteration. It does this by testing either whether the function value at the midpoint is within the tolerance or whether the estimated error from the interval width is small enough. If either test passes, the method returns the midpoint, the iteration count, and a true value indicating successful convergence. In the bisection method, the solver checks whether the function changes sign between the lower bound and the midpoint. If it does, the root is in that half, so the upper bound is moved to the midpoint. If not, the root is in the other half, so the lower bound is moved to the midpoint. Repeating this update steadily narrows the interval containing the root. If the solver reaches its maximum number of iterations without meeting the tolerance, it returns the current midpoint, the iteration limit, and a convergence flag showing that it did not converge. This feedback helps explain why the solver stopped and supports debugging. A tuple is created to store 3 input values for a heat balance calculation. These values represent a realistic scenario: a mass flow rate of 2.0 kilograms per second, a specific heat capacity of 4.18 kilojoules per kilogram per degree Celsius, and heat transfer of 250 kilowatts. Together, they provide the solver with the key parameters needed for the calculation. A bisection solver is used to find the temperature rise in a heat exchanger by driving the heat balance residual to 0. The search starts between 0 and 100 degrees Celsius, with a tolerance of 1 times 10 to the negative 6 and up to 30 iterations. The problem's case parameters are passed into the residual calculation, and the resulting root represents the equilibrium temperature. The bisection solver's result is separated into 3 useful pieces: the estimated temperature, the number of iterations used, and a true or false value showing whether convergence was reached. This makes it easy to use both the solution and its diagnostic information later in the code. The output summarizes the bisection solver by showing the estimated temperature in degrees Celsius to 2 decimal places, the number of iterations it needed, and whether it successfully converged within the required tolerance. This example shows how the program handles invalid input ranges without crashing. It tries to use the bisection solver on a heat balance residual function, but the chosen bounds may not contain the required sign change. If that causes a value error, the program catches it and prints a handled error message. This keeps the program running smoothly even when the initial solver inputs are invalid. This example tests how the bisection solver behaves when it cannot converge within strict limits. It uses the heat balance residual as the target, a starting range from 0 to 100, a very small tolerance, and only 3 allowed iterations. The goal is to confirm that the solver reports non-convergence clearly instead of crashing. This line reports whether the limited bisection solver run converged. It uses the solver's convergence status from its returned result and prints a clear message showing whether a solution was found within the set limits. This script uses the bisection method to solve a heat balance problem and estimate the temperature rise in a heat exchanger. It reports the estimate, the number of iterations, and whether the solver converged. It also demonstrates error handling when the starting bounds do not contain a sign change, and shows how limited iterations can lead to non-convergence without crashing the program. In this lecture, you learn to implement simple iterative methods for solving engineering equations, evaluate convergence behavior using tolerances and iteration limits, and package numerical procedures into reusable Python functions. In the next module, Module 4, we will go over none. Thank you for your attention. See you all in the next lecture.